Hello everyone, in this video we'll be solving problem 48, rotate image. The problem statement is, we are given an n by n two-dimensional matrix that represents an image and we need to rotate the image by 90 degrees clockwise direction. The original image in example number 1 contains 1 in the top left element or position while 9 in the right bottom position. After rotating the image 90 degrees clockwise, 1 should be shifted to where 3 is, while 3 should be shifted to the position where 9 is, and 9 will be moved to 7. I have only highlighted few numbers, but the entire grid or matrix needs to be shifted. Similarly, in example number 2, where the grid is of size 4 by 4, all of the elements are shifted to its right. So this 5 which was at the first element was shifted to the last element in the first row, while 11 being the last element in the first row was shifted to the last element of the entire grid. As an added constraint, the problem statement is asking us to solve the problem using in-place operation. That is, we cannot use additional memory to solve it and instead update the existing matrix, that is the input, to complete this operation. I hope you are able to understand the problem statement. Let's switch to whiteboard and discuss the solution. If we ignore that in-place operation requirement, solving this problem would be very easy. All we need to do is create a new two-dimensional array, run an iteration on the original input while making sure the values are being shifted 90 degrees to its right or clockwise direction, and update the values in this new dimensional array. And once the iteration is done, we can simply return this as our output. The only challenge with this approach is the space complexity, which will be O of n square, as we are creating this two-dimensional array to process all of the elements. The efficient way to solve this problem is not very intuitive and it did not come to me directly. It took me some time to understand the theory before I could start implementing it. One optimal way that we will be using to solve this problem includes two steps, where the first one is to apply the transpose operation on the given matrix and following up with reversing the columns using a vertical split, that is swapping the columns. Now let's discuss each of these operations individually to get a better idea. Transpose operation is where we convert the rows into columns and create a new grid or update the existing matrix. For example, if we use the matrix in front of us, the values 1, 2, 3, 4, 5, 6 and 7, 8, 9 are all of the rows, and after applying the transpose operations, they will be converted into columns. Starting with the first row, that is 1, 2, 3, which becomes the first column. Following that is 4, 5 and 6, and after that is 7, 8 and 9. Now let's compare the two matrices with each other, which will help us identify the rules transpose the original matrix programmatically. Starting with the elements in the diagonal, they remain the same. That is 1, 5, 9, 9 are at the same position in the original version as well as the transposed version. And if we look at the values that were swapped, there is also a pattern in their position. For example, the original position for 2 is 0, 1, 0 being the row and 1 being the column, but for 4 it is 1, 0. If you look at the position of 2 in the new matrix, it is exactly the opposite, that is the reverse version of I and j, where column is 0 and row is 1. Let's look at the position for 6. The original position or index is 1, 2, but after swapping it with 8, the new position is 2, 1, which is exactly the reverse version of I and j values. By swapping the values of I and j, we can easily create a transposed version of the original matrix by in-place operation. I hope you are able to understand the logic on how to apply the transpose operation programmatically on any two-dimensional matrix. Now let's discuss the second operation, that is reversing the column. In this operation, we are basically dividing the entire matrix by drawing a line at the center and then swapping the columns on the left with the right. In other words, the column that starts with 1 is swapped with the column that starts with 7. After swapping the rows, the updated matrix would look something like this. As you can see, the last column 7, 8, 9 has been moved to the first column, while the first column 1, 2, 3 was shifted to the last one. If we compare the swapped column version with the original input, you will see that all of the elements were shifted in the clockwise direction by 90 degrees. For example, the number 1, which is at the first row first column, has been moved to the first row last column, while 3 was shifted to the last element, that is last column last row. The same applies with the remaining numbers in the matrix. With this solution, our time complexity is O of n square, as we are iterating through all of the elements in the given matrix multiple times, first to run the transpose operation and the second one to reverse all of the columns. While the space complexity is O of 1, as we are not using any additional memory for calculations and instead doing in-place operation. I hope you're able to understand this explanation. Let me show you how we can implement the very same approach using Java. In this Java implementation, I've broken the solution down into two steps, starting with applying the transpose operation on the original matrix. Here I am running two for loops to iterate through all of the elements using two pointers I and j, and inside the nested for loop, I am swapping the values that are saved at I and j position using this temporary variable. Once the swapping is complete, the next step is to swap all of the elements in the row. So for that, I am running a for loop to iterate through all of the rows and calling this helper function. This helper function uses a two-pointer approach to iterate through all of the elements. The first pointer is pointing at the leftmost element, while the second is pointing at the last element. Using these pointers and a temporary variable, I am swapping the values that the left and the right pointer is pointing at, and later on incrementing the left and decrementing the right pointer. As we are doing an in-place operation, all of the values are saved back into this matrix variable at the end. This code, when submitted on LeetCode, beats 100% of the submissions in terms of runtime and 14% in terms of memory. Thank you for watching this video. I hope you are able to understand the explanation. The details to access the source code is available in the description below. Feel free to check that out, and I will see you in the next one. Thank you.